So on the chapter 5 through 7 review, I'm going to focus mainly on reviewing chapter 5 since it's been a lot longer since we've seen that material. I'm still going to review a couple things from the most recent chapters, but most of this is going to be reviewing chapter 5. So on the first 6 questions, those are the chapter 5 questions. And I'm going to give you 2 options to solve or find the probabilities for each of the questions. So I'm not going to have room to write the sentence, but one thing you will have to do, so numbers 1 through 6 also need a sentence. Now, the sentence for 1 through 6 are just writing the probability in the context of the problem. So it's not like the sentence is super detailed. It's just a short statement saying this is what this probability means. On the first problem, we have that on a certain day at a store, the average profit made is $360 with a standard deviation of $50. Assume the distribution is normal. What is the probability that X is greater than $400? So anytime you have a probability with a mean, you have to figure out if it's for a single mean or for a sampling distribution for means. And it's all based on whether or not you're given an n, which is a sample size. And in this case, we just have a single store, so this is just a regular probability. So the first option is to calculate your z-score to find the probability. So the z-score is your x value, which comes from your probability statement question. So 400 minus your mean, 360, over the standard deviation, which is 50. So we get 40 over 50, which is a z-score of 0.8. Now we go to normal CDF. Because our probability statement is a greater than, the lower bound is 0.8, upper bound of 1E99, and then the mean is 0 and the standard deviation is 1. And we end up with 0.2119. Option 2 is to use your mean and standard deviation, and you just go straight to normal CDF. So we go straight to normal CDF, and then we use our probability statement to determine our lower and upper bounds. So because we're doing greater than 400, our lower bound is 400. The upper bound is 1E99. We use our mean of 360 and our standard deviation of 50. And we're going to get the same probability of 0.2119. So it doesn't matter which option you use, you will get the same probability. And even if they're slightly different because of rounding, I would still give credit based on whichever method you used. And then for a sentence here, you would just say the probability the profit is more than $400 is 0.2119. So that's all you need for a sentence. In our second question, we have the time it takes students to complete a statistics quiz is normally distributed with a mean of 65 minutes and a standard deviation of 12.5 minutes. What is the probability that a random sample of 25 students will have a mean completion time greater than 68 minutes? So my first step here is to write my probability statement. So we're trying to find the probability that X bar is greater than 68. And the reason I'm using X bar here instead of just X is because now I have a sampling distribution. I have a sample size. So we're not looking at a single thing, we're looking at entire sampling distribution. So for option 1, which is to calculate the z-score. The numerator doesn't change. My numerator is still going to be the value from my probability statement, 68 minus my mean, which is 65. The standard deviation is going to change though, because I need to calculate the sample standard deviation for my distribution. So we take the 12.5 and we're going to divide it by the square root of our sample size, which is 25. So that's going to give us 3 over 2.5, which gives us a z-score of 1.2. So for normal CDF, lower bound is 1.2, upper bound 1E99, mean of 0, standard deviation of 1. And we're going to get 0.1151. For option 2, where we use our mean and standard deviation, the first thing I actually have to do is calculate my standard deviation. So I have to do 12.5 divided by the square root of 25, which is 2.5. I don't use the 12.5 as my standard deviation. Now we go to normal CDF. The lower bound is going to be 68, upper bound 1E99, and then we're going to use our mean of 65 and our new standard deviation of 2.5. And we get the same probability, 0.1151. Our third problem says Dan makes money doing lawn care during the summer, assuming that he makes on average $240 with a standard deviation of $60 and the distribution is normal. What is the probability he makes less than $255? So for our probability statement, because we're looking at a single person or outcome, the probability is just X less than 255. So for option 1, we're going to have Z equals 255 minus 240 over 60, which is going to give us 0.25. When we go to normal CDF, because we're trying to find the probability that we're less than, our lower bound is going to be negative 1E99, and our upper bound is going to be our 0.25, mean of 0, standard deviation of 1, and we get 0.5987. Option 2, where we use our mean and standard deviation. So again, because our probability is a less than, the lower bound is negative 1E99. The upper bound is the 255, mean of 240, standard deviation of 60. We still get 0.5987. So this is going to be our last example of a distribution for means, and then we'll do a couple examples with proportions. So we have the incomes in a certain large population of college teachers have a normal distribution with mean $60,000 and a standard deviation of $5,000. 25 teachers are selected randomly to serve on a salary review committee. What is the probability that their average salary exceeds $62,500? So for our probability statement, because we're given a sample size, it'll be X bar greater than 62,500. And then option 1, we'll have z equals 62,500 minus 60,000 over 5,000 over the square root of 25. And that's going to give us a z-score of 2.5. So when we go to normal CDF, lower bound 2.5, upper bound 1E99, mean of 0, standard deviation of 1. And we're going to get 0.0062. For option 2, first thing we have to do is calculate our standard deviation. So we're going to do 5,000 divided by the square root of 25, which is 1,000. Then we go to normal CDF. The lower bound is going to be 62,500, upper bound of 1E99, mean of 60,000, and standard deviation of 1,000. And it still results in a p-value, or a probability, of 0.0062. So one of the things from chapter 5 we have to differentiate between is if we're looking for looking at a sampling distribution for means, so that means we have a sample size n, or if we're looking at a single mean. All right, next two examples to round out chapter 5 are going to be about sample proportions. So we have, suppose that 35% of all business executives are willing to switch companies if offered a higher salary. If a headhunter randomly contacts an SRS of 100 executives, what is the probability that over 38% will be willing to switch companies if offered a higher salary? So for our probability statement, because we're looking at a probability distribution for proportions, this is now p hat, and it's going to be greater than 0.38. So because proportions are probabilities, we do need to write them as our percentages, we need to write them as decimals. The options are still the same as means. So option 1 is still to calculate a z-score. So we'll have z equals 0.38 minus 0.35 in the numerator. For the standard deviation of a proportion, it's the square root of p, so 0.35, times 1 minus 0.35 all over n, which is 100. And that is going to give us a z-score of 0.63. If you wanted to, you could go 3 decimal places and you could say 0.629. It is up to you. I'm not going to be overly picky on if you do 2 or 3 decimals, because if you have a problem like this on the test, I'll just grade based on how you rounded your z-score. And then for normal CDF, our lower bound is our z-score, 0.63, upper bound 1E99, mean of 0, standard deviation of 1. And we're going to get 0.2643. For option 2, now, unlike a distribution for means, a proportion distribution doesn't have a given standard deviation. So you always have to calculate the standard deviation. You have to do the square root of 0.35 times 1 minus 0.35 over 100, which is going to be 0.0477. And then we go to normal CDF. Our lower bound will be 0.38. Upper bound will be 1E99. Then we'll use our mean of 0.35 and our standard deviation of 0.0477, which gives us a probability of 0.2647. Now for proportions, option 2 is going to be more accurate because I didn't round as often. Because when we calculate the z-score, I rounded 2 decimals for my z-score. So I have a very small z-score. If I had rounded 3 or more decimal places for my z-score, I probably would have gotten a probability closer to what I got for option 2, because the only rounding I had to do for option 2 was my standard deviation. And since I always round my standard deviations to 4 decimal places, it made it slightly more accurate. So depending on how you round for z-score, you could get something that's exactly the same as option 2, or you could get something slightly different. And both would be correct. It's not like I would take off for one, but you do have to show your work in either case so I know which method you used. So last problem from chapter 5 says Harley-Davidson motorcycles make up 14% of all motorcycles registered in the United States. You plan on interviewing an SRS of 500 motorcycle owners. What is the probability that your sample contains less than 10% who own Harleys? So we're trying to find the probability that p hat is less than 0.10. So for option 1, we're going to have z equals 0.10 minus 0.14 over the square root of 0.14 times 1 minus 0.14 all over 500. And that will give us negative 2.58. So we go to normal CDF. Our lower bound is going to be negative 1E99. The upper bound is negative 2.58. Mean of 0. Standard deviation of 1. And we get 0.0049. For option 2, when I calculate my standard deviation, we do the square root of 0.14 times 1 minus 0.14 all over 500. And we're going to get 0.0155, which when we plug into normal CDF, we get a lower bound of negative 1E99, upper bound of negative 0.10, mean of 0.14, and our standard deviation of 0.0155. And in this case, because my z-score was larger, it was over 1, rounding 2 decimal places for the z-score actually doesn't change the answer for between option 1 and option 2. I'm still going to get 0.0049. The only time you really have to worry about the option 1 and option 2 not giving you the same answer is if your z-score is less than 1 and a decimal that doesn't end. So if it's an exact decimal, like the first 4 we did, all of my z-scores were exact decimals. So it always matched what I got for either option. But if my z-score isn't an exact decimal and it's a decimal itself, then option 1 and option 2 aren't necessarily going to give the same answer. So that's all chapter 5. The last 6 problems are all chapters 6 and 7. And I don't do an example of everything from those chapters. I do a few of each. Looking back at the chapter 6 and chapter 7 quiz reviews are probably going to be the best bet when it comes to having multiple examples of each type of problem, but I'm only going to review a certain amount. So we're going to start with determining sample size. So we want to determine the sample size needed to construct a 95% confidence interval to estimate the average annual salary of adjunct instructors at Columbus State within $200. Suppose the population standard deviation is believed to be 812. So when we're solving for sample size, we have to figure out, are we solving for the sample size for means or for proportions? So the difference between the two is if it's for proportions, you're going to have percentages. So this is solving for sample size for mean, and the formula is n equals our z critical value times our standard deviation over the margin of error squared. So when I pick out that information from my problem, my margin of error is 200 because it comes from the statement within $200. Our standard deviation is 812, and then our z critical value is going to be 1.96. And in order to get that, you go to INV norm, and then your area is the remaining percent to 100 divided by 2 as a decimal. So 5% divided by 2 is 2.5%, which is a decimal is 0.025. So now I plug that into my formula. We're going to have 1.96 times 812 over 200 squared. And that's going to give us 63.3. Now remember, because we're solving for sample size, we can't have a decimal for n. So no matter what we get from the formula, we have to round up. So in this case, it would be 64. And then you do have to include units. So in this case, it's adjunct professors. You could also use teachers, people, as long as it means the same, because adjunct professors and teachers are pretty interchangeable. They are both types of people, so I'll accept either one. Okay. The next problem says the National Center for Education Statistics surveyed 4,400 college graduates about the lengths of time required to earn their bachelor's degrees. The mean is 5.15 years and the standard deviation is 1.68 years. Based on these sample data, construct the 99% confidence interval for the mean time required to earn their bachelor's degrees by all college graduates. Interpret your solution. So anytime we're doing a confidence interval for means, the first thing we have to determine is whether or not this is going to be a t interval or a z interval. And it's based on whether or not you're given population or sample standard deviation. And because we are given a sample standard deviation, this is going to be a t interval. So when we calculate our t critical value, we go to INVT. The way we find the area is the exact same way we do if we do INV norm. So remaining percent to 100 divided by 2, which in this case would be 0.005. And then we need to do our degrees of freedom. And degrees of freedom is always sample size minus 1. So in this case, it would be 43.99. And then you can either go 2 or 3 decimals for this critical value. So you can say 2.577, or you can use 2.58. Either one, I will accept the confidence interval. So when we set up the confidence interval, we use our mean, 5.15, plus or minus our critical value, 2.577, times our standard deviation, 1.68, over the square root of n, which is 4,400. So that becomes 5.15 plus or minus 0.0653, which when we add and subtract gives us the interval 5.085 to 5.215. And then the last step is to write our sentence. So we are 99% confident that the true mean time to earn a bachelor's degree by all college graduates is between, and then because this is a confidence interval for means and not proportions, we do need to include units when we get to this step. So it'd be 5.085 years and 5.215 years. If you just want to put years once and you put it after the second number, I'm not going to count that wrong as long as years appears in your interpretation sentence after your numbers. Next, we're going to talk about a confidence interval for proportions. So we have that out of 210 bagels that were made fresh at Panera Bread, 30 of them were thrown away because they weren't sold. Construct a 90% confidence interval for the true proportion of bagels that were thrown out each day. So the first thing I actually need to do when I'm doing a confidence interval for proportions is to calculate my p-hat. Sometimes it might be stated in the problem. Other times it might be a similar situation where you have to calculate it. So we'll do 30 over 210, which unfortunately is not an exact decimal. So I like to go 4, so 0.1429. The minimum requirement is 3 decimals. So you could also use 0.143. You cannot use 2 decimals unless the probability is exactly 2 decimals. Then we calculate our z critical value. So we're going to go to INV norm. And then we're going to have an area of 0.05. And again, you can either use 1.645 or 1.64. Either one works. I would grade your confidence interval based on that. So we do p-hat, which is 0.1429. Plus or minus our critical value, 1.645, times the square root of 0.1429 times 1 minus 0.1429 all over n, which is 210, which then becomes 0.1429 plus or minus 0.0397, which gives us the interval 0.1032 and 0.1826. Make sure when you're writing your confidence interval, you always put the smaller number first and the bigger number second. Then for our interpretation, we are 90% confident that the true proportion of bagels thrown out each day is between 0.1032 and 0.1826. You are allowed to, for your sentence for a proportions, write your confidence interval numbers as percentages in the sentence. So if you wanted to say 10.32% and 18.26%, that would be correct and I wouldn't count it against you. The one thing that I am not doing on the review is a difference in means or a difference in proportions confidence interval. So if you want to practice one of those, go back to the quiz reviews for chapter 6 and chapter 7, or the notes or the assignment, and you can find an example if you would like to practice a difference in means or a difference in proportions confidence interval. All right. Next, we're going to talk significance tests. And then also type 1 and type 2 errors. So we have a supplier of TI-83 calculators claims that the average life of their calculators is 8 years. A sample of 12 calculators reveals the following lifetimes in years. Test the claim that the supplier's calculators do not have an average life of 8 years at the 0.05 level of significance. And then we're going to discuss the type 1 and type 2 errors in the context of the problem. So because this is a significance test, my first step is to write our null and alternative hypotheses. So our null hypothesis is going to be that mu equals 8, which is their claim. The alternative hypothesis is going to be that mu does not equal 8. So in the question, it says do not have an average life of 8 years. So that tells me that my alternative hypothesis is does not equal. So we're not trying to show specifically that it's more than or less than, just that it's not 8. Now I need to actually calculate my X bar and my sample standard deviation. So in order to get those, we're going to type those numbers into list 1, and then we're going to go to one variable stats. And when we do that, we'll get a mean of 7.808 and a standard deviation of 0.2778. So enter data into list 1 and go to one variable stats. All right, once we have our sample mean and sample standard deviation, we're going to calculate a t-test statistic. So remember, similar to confidence intervals for means, significance test for means, you also have to know whether or not you're doing a t or a z test statistic. And it is, again, based on whether or not you're given population or sample standard deviation. So our numerator is going to be 7.808 minus 8. And our denominator will be our sample standard deviation, 0.2778, over the square root of n, which is 12. We get t equals negative 2.39. So because we calculated a t-test statistic, that means to get our p-value, we have to go to t-CDF. And our lower bound is going to be negative 1e99, and our upper bound is negative 2.39. So for t-CDF, remember, the sign of your test statistic matches which 1e99 you use. So negative test statistic, negative 1e99. Positive test statistic, positive 1e99. And then our degrees of freedom, so it's still sample size minus 1. In this case, that would be 11. So we end up with 0.0179, but this is not our p-value. So because our alternative hypothesis does not equal, we have to double this number, and our p-value is 0.0358, which is less than alpha, which is 0.05. So double p-value when HA does not equal. And stuff like this is something that you can put on your sheet of notes. So things like how to enter your data into list 1 and find mean and standard deviation. When should you double your p-value? Those are perfect things to write on your sheet of notes. And then our conclusion is going to be reject. So if you're not comfortable with when to reject or fail to reject, write it down. So you reject the null hypothesis when the p-value is less than alpha, fail to reject when the p-value is greater than alpha. And then our sentence. So our sentence would be, there is enough evidence to show that the supplier's calculators do not have a life of 8 years. The rest of what I'm going to do is related to type 1 and type 2 errors. So I'm going to kind of separate the hypothesis test stuff from the type 1 and type 2 error stuff. So when it comes to a type 1 and a type 2 error, so a type 1 error is when you reject but should have failed to reject. And a type 2 is the exact opposite. So failed to reject but should have rejected. So if you are struggling with remembering the difference between a type 1 and type 2 error, write this on your sheet of notes. So for the interpretation is in the context of the problem. So for a type 1 error in this problem, rejecting would mean you determine the calculators do not have an average life of 8 years, but you should have failed to reject. So then you would say when they do. And then our type 2 error would be the opposite. So you determine the calculators do have an average life of 8 years when they don't. All right, so the next we're going to take a look at is a hypothesis test for a single proportion. So Columbus State Community College claims that 42% of the students are male. A random sample of 48 students counts only 12 males. Test to determine if the proportion of males is significantly different, either higher or lower, from the claim at the 0.04 level of significance. So this time when we do our hypothesis test, because it's a proportion, we're going to have P equals. So our null hypothesis has to be P equals 0.42. Our alternative hypothesis, because it states significantly different, that would mean that our alternative hypothesis does not equal 0.42. And then we do need to calculate our P hat, which in this case would be 12 over 48, which is 0.25. And then we calculate our z-test statistic. So we'll do 0.25 minus 0.42 all over the square root of 0.42 times 1 minus 0.42 all over 48. And that gives us negative 2.39. Now we go to normal CDF for our p-value. Our lower bound is going to be negative 1e99. Upper bound is going to be negative 2.39. Mean of 0, standard deviation of 1. And that's going to give us 0.0084, which again, because our alternative hypothesis does not equal, we need to double, which is 0.0168. And because our level of significance is 0.04, that is still less than alpha. So we are going to reject our null hypothesis. If my alpha had been 0.01, then we would have failed to reject, because our p-value then would have been greater than that. So for our sentence, there is enough evidence to show a significant difference in the proportion of males at Columbus State Community College. And then our last example. So we have ultrasound is often used in the treatment of soft tissue injuries. In an experiment to investigate the effect of ultrasound and stretch therapy on knee extensions, a range of motion was measured before and after treatment for a random sample of physical therapy patients. The data appears in the table below. Test the claim that ultrasound and stretch therapy improves the patient's range of motion. Now, this is not a difference of means significance test. And the reason being is because we are performing our test on the same individuals. So we have one population. So this is actually an example of a paired T procedure. So not a difference of means, it's a paired T procedure, which means we're actually looking at the mean difference. So we have to define the difference that we're looking at. I always like to define my difference based on which numbers are bigger so I can kind of avoid negatives. So I'm going to define it as post-treatment minus pre-treatment. So for the null hypothesis, we're going to have that the mean difference equals 0. So that would indicate that there's no change in range of motion between pre and post treatment. The alternative hypothesis, so if I'm looking at my problem, it does say we want to know if it improved the patient's range of motion. So that would mean that our mean difference would be greater than 0 because their post-treatment score should be higher than their pre-treatment, which means their difference should be positive. So depending on how you define that mean difference, that affects your alternative hypothesis. The next step is then calculating that sample mean and sample standard deviation. So because it is a mean difference and not a difference of means, we have to do a third list. So I'm going to define list 1 as my pre-treatment and list 2 as my post-treatment, which means when I do my difference, I have to go into list 3 and define list 3 as list 2 minus list 1. And once I do that, then we go to one variable stats. And we're going to get our mean of 3.43, and we're going to have a standard deviation of 3.51. So we're going to calculate one var stats for L3, which equals L2 minus L1. Again, this is the perfect type of thing to put on your sheet of notes. All right, so this is, because it is a sample mean and a sample standard deviation, this is still a t-test statistic. So we're going to do 3.43 minus 0 over our sample standard deviation, 3.51, divided by the square root of n, which is 7. That's going to give us a t-test statistic of 2.59. So we go to t-CDF. We have a lower bound of 2.59, an upper bound of 1E99, mean of 0, standard deviation of 1, and we get a p-value of 0.0206. Now, I need to figure out what alpha I'm comparing that to, and I don't state an alpha in the problem. So we always use an alpha of 0.05 when it's not stated. And that ties back into type 1 and type 2 errors. So this is less than our alpha of 0.05, which means we are going to reject our null hypothesis. And we'll say there is enough evidence to show ultrasound and stretch therapy improves range of motion. So again, I didn't give any problems where you had to do difference in mean significance tests or difference in proportion significance test. So again, if you want to practice those, look back at the Chapter 6 and Chapter 7 quiz reviews, the assignments that covered that, so you can practice either of those two things. So let me know if there's any other questions you have from Chapters 5 through 7 before the test.